So for tonight's event, I'm pleased to introduce Professor John Marshall, the Cecil and Ida Green Professor of Oceanography in the Department of Earth, Atmospheric and Planetary Sciences, which is hard to say, so they call it EAPS. John conducts research in climate science and the general circulation of the atmosphere and the oceans, which he studies through the development of mathematical models. In fact, he's in charge of MIT's Climate Modeling Initiative and the coordinator of Oceans at MIT, which is a new umbrella organization dedicated to all things related to the ocean at the Institute. So please welcome Professor Marshall to talk to us about the elephant in the climate.
I'm going to review global observations of warming trends. So just to start off, looking at the observations and not just atmospheric observations, but what we know about the temperature trends in the ocean. And these, it turns out, are a key part of the puzzle, the global warming puzzle. What's going on in the ocean, and how does that relate to the atmosphere? And what we're going to find is that what I'm going to describe is that we think that the oceans are warming up, and they're of course becoming more acidic because atmospheric concentrations of CO2 are going up. CO2 dissolves into the ocean, and the oceans become a little bit more acidic. And because the oceans are warming up, the water column expands, warm water expands, and so sea level is rising. The second thing I'm going to talk about is the timing and regional patterns of warming. So the Earth, as it warms up, is not doing so in a uniform way. Parts of it are warming up more rapidly than others. And the ocean is playing a huge role in setting the spatial patterns of warming and the timing of the warming. So if we began to, if the Earth warmed for whatever reason, its temperature is going to increase. The rate of increase depends essentially on the heat capacity of the climate. And the ocean is the biggest, we mentioned an elephant, right? The ocean's a huge heat capacity, so it's controlling the rate at which the atmosphere is warming up. Not controlling it, but it's playing a big role in that. So the Earth's not warming up uniformly, and the ocean plays a central role in setting the patterns and timing of the warming. And I'm going to explore some of the underlying mechanisms using some models that we've developed, models of the climate. Now, so this first part is mainly observational. The second part, I'm going to begin to use some models. Who hasn't heard of has anybody not heard of the warming hiatus? So that in the last 10 years, global mean temperatures have not been rising quite as fast as they were prior to that. So there's a hiatus. The Arctic appears to be warming more rapidly than the Antarctic. So why is it the Antarctic's not warming as fast as the Arctic? And ocean currents are changing subtly, not radically, but they are changing as the ocean warms. And then I'm going to conclude and try to describe what's happening and why is it happening and what might happen in the future. So what I'm going to show you is maps of surface air temperature change. And these are observations, global observations of annual means relative to a 1950 to 80 average. And so the kind of yellow areas are 1 degree centigrade to 2 Fahrenheit. And of course this is relative to this average. And here is a time series. This red is, I think it's a 5-year running mean, and these are the annual values. This is the global mean. So starting in 1950, coming up towards the present day. And I'm going to show you a movie of this. This is air temperature. So 1951, 1952, etc. So here. So there's variability, of course, and we're moving along here. It's fairly flat, 1950s, 60s, 70s, and then it begins to trend upwards, 79, 70, 1984, 5, 7, and we're getting up to the present day. And can you see how it's becoming much redder in the north? So relative to this 1950 to 80 average, the temperatures are much higher. The global mean temperatures have gone up, and the northern hemisphere has warmed up much more than the southern hemisphere. Now, this is partly due to the fact that the land has a smaller heat capacity than the ocean, and so this is a transient problem. And so the heat capacity is smaller, and therefore it tends to warm up more over land. That's why we see the red regions in the north. But in the south, where there's not a lot of land, you can see that the temperatures haven't changed very much, or even have cooled. And what I want to talk about is the role of the ocean in playing out this, helping to set some of these regional patterns in temperature. Now, this is from the New York Times just on Saturday. So there was in 2014, it was the hottest year on record. There's even a debate about that because the error bars, there are some error bars on it, and the error bars, you could debate whether it's the hottest, but it's right up there. And this shows you how far above or below the average temperature we were in 2014. So again, you can see that the northern hemispheres have warmed up more. The southern hemisphere around Antarctica has not warmed up hardly at all, or in fact it's cooled slightly. And there are these patterns. And so this is the average global surface temperature going from 1880 up to the present day. And so we can see this warming trend. This is the famous hiatus that literally hundreds of papers have been written about in the last few years about why is it that as our greenhouse gas forcing goes up in the atmosphere, why is it that the global mean temperatures have flattened out in the last 10 years or so? I will say something about that in a moment. So there's no debate. In fact, I was told over dinner this evening that in fact the Senate had taken a vote on this today or something, and that even the Senate had actually agreed that we were warming up. Is that true, or is that a scurrilous rumor? We're warming up, right? So where's the heat coming from? So we could think about where the heat is coming from, and there are two possibilities, at least two main possibilities. One is that there's a radiative imbalance at the top of the atmosphere, so that we have the sun, incoming solar radiation and outgoing long-wave radiation, and that there's been some change to the balance. So, for example, due to greenhouse gases going into the atmosphere, the outgoing long-wave radiation might have gone down slightly, so that there's a net warming. Some people have discussed whether the solar constant is actually changing. The solar constant does vary, but it varies by a rather small amount, order 1/10 of a watt per meter squared, and globally averaged around the Earth. And in fact, in the last 30, 40 years, the sun has been slightly cooling. It's been putting out less energy in the last 30 odd years. So that's one possibility. The other possibility is that the heat is coming from the ocean. So the ocean has a huge amount of heat. The heat capacity of the ocean is enormous. That's where most of the heat is. And so, the ocean could give a little bit of that heat to the atmosphere. The atmosphere could warm up, and therefore the ocean ought to cool down. So, so there's the arrow coming up from the ocean. Those are the two possibilities. And so this has motivated oceanographers and the climate community to look at how the heat content of the ocean has been changing over time. And so I'm going to talk a bit about measuring the heat content of the ocean. And this is how we used to measure the heat content of the ocean. We would go out in a ship and take these long lines. These are known as hydrographic sections. Research ships running along long hydrographic sections of temperature and salinity. And from this matrix of measurements, one can come up with some estimate of the heat content, say, of the ocean. Now you can see that it's a coarse grid. This is from the World Ocean Circulation Experiment that actually Carl Wunsch, what I was talking to some of you alums over lunch, over dinner, and at least one of you know who Carl Wunsch is, a very famous oceanographer at MIT. And he was one of the organizers of the World Ocean Circulation Experiment that happened in the 80s and 90s. And they laid out this track of organized paths in the ocean to measure what was going on there. Now, so this is how we used to do it, say, since the Second World War up to the present day. This is how we do it now. So this is known as the Argo array. And so essentially, each of these red dots is a device which is known as an Argo float. These were the brains and the drive behind these floats is Breck Owens at Hui and Dean Remick at Scripps. And these Argo floats are thrown in. Let me show you so you can see them moving around here. So this is the number of floats gone in. This is the year 2002. This is May, June 2002. This is the number of floats. You can see the floats going in. Each one costs about $15,000. We've got about 4,000 of them out in the ocean at the moment, and they hang around at 2 kilometers down, and every couple of days come up to the surface, measuring temperature and salinity, and then beaming it back, and then they go back down again. And so we now have this global network of observations of the ocean. This is 2006, so here's the thing. This is I don't know, a few million a year to do this, and it's revolutionized the field. These are just a profile of temperature and salinity. So we can can you see that there's an ice edge here? So some of the floats can't deal with ice, so as they come to the surface, if they hit their head underneath the ice, that's it. And they go down and they've gone forever. But we're trying to devise ones that will kind of hit their head under the ice and say, okay, no, I can't get up there, so I'll move over here. And, move. And we want ones that can go deeper, and also floats that can measure the biogeochemistry of the ocean. There's a very interesting project now coming out of Princeton, led by Princeton University, where they're measuring in the Southern Ocean some of the biogeochemistry. So this is just wonderful for our field. And it's technology, the engineering of the ocean, the robotics that enable this kind of thing to happen is wonderful. So this is the kind of data that we're dealing with. These started from around 2003 onwards. And so what can we do with this? So I'm going to show you the observed ocean temperature change from early 1950s up to the present day, relative to a 1950 to 1980 average. And so this is this does not in 1952 we didn't have any Argo float. So this data is noisy, gappy, and it's been interpolated. So we have to bear that in mind. So we now, so I'm going to click this and it will begin to move forward. So this is, now we're looking to see whether the ocean warms or cools. So 1967 onwards. And so you can see that this is 0.2 degrees, 0.4 degrees. As the time goes on, you can see the kind of warmth at the surface moving down into the interior. So the ocean is actually warming up. Do you want to see that one again? Yeah. Okay, so this is sign of latitude, so that gives you some idea of area. So the 60 to 90 is compressed on this scale. So the ocean's warming up, and it's roughly 1/4 degree to a depth of 1 kilometre in the last 50 years. That's very significant because it means that the heat is not coming from the ocean. Where's that heat in the ocean coming from? You can see it coming down from the surface, right? It's coming down from the surface. So that's 2010. Look at all that heat at the surface. So it's warming up by roughly 1/4 degree to a depth of 1 kilometre. So I surmise from that the heating is coming from the atmosphere. And actually that's quite consistent with greenhouse gas warming of the atmosphere. So I'm going to put some numbers in, and this is just a back of the envelope calculation. Think of yourselves as undergrads or something, and I'm doing a back of, this is your first take on the thing, and I'm doing a back of the envelope calculation. Now this is really a complicated inverse problem where you have to jiggle error bars and do complicated inversions. But this is a back of the envelope calculation. So what I'm going to do is say that I'm going to imagine that the ocean has a density rho and a specific heat c, and the depth to which the heat is sequestered, order a kilometre, is h. And so the rate of change of the heat content is rho ch dt dt. That's the rate of change of heat content, and we can get that from observations of the oceans warming up. And then that's going to give me a Q, which is a rate of heating of the ocean due to heating through the sea surface. The geothermal effects, you could argue that it was geothermal effects which were heating the ocean. First of all, you'd see the heat coming in from the bottom, and also geothermal effects are milliwatts. I'll show you in a moment that the heat coming in is order a watt per metre square coming in at the surface. So there's a radiative, now the rate of heating is the radiative forcing R, which is the downwelling radiation from the atmosphere, because the atmosphere's equilibrium is being perturbed. And then there's, if you warm something up, it pushes back, it tries to radiate that energy back out again. And so there's a minus lambda T. And this lambda is known as the climate sensitivity. And if we took a vote on this in the climate change community, many people would say that one of the biggest challenges to understand the climate is what is the climate sensitivity of the climate? How much does it change? What does it depend on, etc. So anyway, there's the radiative forcing, and then there's the damping to space because the ocean's warming up. So I'm going to put some simple numbers in here. So if this is 0.5 degrees centigrade over a kilometre in 100 years, if you do the sum, you get 0.6 watts per metre squared. 0.6 watts per metre squared of heat is the net forcing averaged over the globe. And that's made up of order 1 watt per metre squared of radiative forcing, and this damping term, order 0.5 watts per metre squared. So 1.1 minus 0.5 is 0.6. So this says that the radiative forcing perturbation, which I think is due to greenhouse gases going into the atmosphere, is order a watt per meter squared in broad numbers, about a watt per meter squared. And I'm going to try to give you some concept of what a watt per meter squared is. So if you think of a 50 watt light bulb, you know, it's drawing 50 watts out of the power supply, and it's lighting a room of dimension 7 by 7. A 7 by 7 meter by 7 meter kitchen is pretty big, right? But anyway, my two-car garage. Yes. So you've got a 50 watt light bulb shining in a 7 by 7 meter room. That's going to give you an average 1 watt per meter squared. One of the things we do in our climate modelling at MIT is we project spheres onto cubes. And we do that because a cube maps onto a parallel computer beautifully. So we can map the faces of cubes onto parallel machines, and we can subdivide these grids. But now imagine that each one of those is a little room by 7 meters by 7 meters, and there's a light bulb, a 50 watt light bulb shining all the time, everywhere, all the time. That's going on for 50 years. Then what's going to happen is that the ocean's going to warm up a bit. And that's basically what I think is going on. Everywhere, all the time, we've got this radiative imbalance. So what's the implied sea level rise if you take a column of water of depth h and you warm it up by an amount delta t, it stretches by an amount h, and little h over big H is alpha delta t, where delta t is the temperature change, and alpha is the thermal expansion coefficient of water, which is 2 times 10 to the minus 4 per Kelvin. So if you put the numbers in, if I warm up the ocean by a kilometre of ocean by a delta T of half a degree, and this is the thermal expansion coefficient of water, I get 10 centimetres. So that would say that in 100 years, if we warm the ocean at this rate, it's going, just by the so-called steric effect, it's going to expand by about 10 centimetres. Now, if we look, this is courtesy of my colleague Patrick Heimbach at MIT. So if we look at sea level change, lots of error bars here, that we have tide gauges. This is up in the contemporary period, or the instrumental period. And then in the last 20 odd years, we have the satellite altimetry. So we're measuring the height of we're measuring sea level from space very accurately. And in the satellite era, the sea level's been going up by 3 millimeters per year, which is about 30 centimeters per century. If you multiply 3 millimeters by 100, you get 30 centimeters. So during the satellite era, which is a very short period of time, sea level seems to be going up a little bit more than we might expect from simply a steric effect. Now, these are projections into the future. So this is the current time, and these are various projections into the future. And basically, there's a huge uncertainty here in sea level. Anybody got any ideas on why there's such uncertainty? I mean, it is the future, but we can actually predict probably reasonably well how much heat is going to go into the ocean. If we make a projection about how much carbon dioxide is going to go into the atmosphere, we can figure out how much the ocean's going to heat up. But the biggest uncertainty is what's happening to the cryosphere, to the ice. So if you have ice, sea ice, floating in water, and it melts, the level of the beaker doesn't change, by Archimedes. But if you have an ice sheet resting over land, and that melts and flops into the ocean, then sea level will go up. And so the reason that there's such uncertainty here is in our projection, the community's projections into the future, is that we don't understand. It's very hard for us to model how ice sheets interact with the bedrock on which they're, and how the ocean might be lapping and warming the ice sheet. That's the reason that there's such a huge spread in the future projections of sea level. It's the uncertainty in what's happening to the land ice. Now, where is this 1 watt per meter squared coming from? Why might we expect there to be order 1 watt per meter squared radiative forcing of the climate? And we think that the community thinks that it's due to anthropogenic forcing of climate. So this shows you the effective radiative forcing in watts per meter squared. So this is 0. This is 2 watts per meter squared, minus 2 watts per meter squared. And these kind of processes cool the atmosphere, and these warm the atmosphere. So these are, this is CO2, carbon dioxide, a triatomic molecule which has rotational and vibrational bands which interact very strongly with the long wave radiation that a black body radiating at 255 is going to interact, the radiation stream coming from that's going to interact very strongly with triatomic molecules. So this is as a function of time, though, this is the CO2 going into the atmosphere. And there are other greenhouse gases, particularly methane, tropospheric ozone, triatomic molecule due to pollution effects. So all of these things lead to growing perturbation of the radiative balance of the atmosphere and climbing up to over 2 or 3 watts per meter squared. Now there are things which cool the atmosphere. Some of our activities cool the atmosphere, one of which is aerosols. So Dan Sitsko, for example, is a great authority on aerosols. He flies aircraft into clouds and looks at how the clouds are nucleating and looking at the particles. So the aerosol effects are about a 1 watt per meter squared of cooling. And these are made up of radiative effects. So aerosols just scatter and reflect back out to space the incoming solar radiation. The other thing aerosols do is they lead, the little particles allow water droplets to nucleate on them and they create clouds. So if you have a polluted atmosphere or an atmosphere with lots of aerosols, there's more cloud, and that cloud reflects the incoming solar radiation. So these things cool the atmosphere, and then there are these volcanoes, Krakatoa, Pinatubo, El Chichar, etc. So these are spikes of aerosols going up into the atmosphere, leading to cooling. So the net effect of this is, guess what? Order 1 watt per meter squared. There are uncertainties in there. The solar forcing. This is the sunspot cycle. This little yellow thing there is the solar forcing, and we think that that's not an external driver on these timescales. So there's a kind of what Jim Hansen in Goddard has called a Faustian bargain, and that is that, a contract with the devil, that if we actually clean up the atmosphere, we get rid of the aerosols and we're going to warm even faster. So there are 2 things fundamentally cooling the atmosphere. One is the ocean taking heat out of the atmosphere into the interior, and the other are aerosols. Those are the 2 things which are counteracting, we think, the greenhouse gas forcing. But anyway, so you can do Green's function calculations with climate. So what you do is you imagine the climate is at equilibrium. We instantaneously increase the radiative forcing of the atmosphere. So it's a step, it's an impulse. It goes a step function. And then what we look at is how the system responds to that. So you're doing, if I want to know what this is made of, I'm going to hit it, see what happens. And so we can do that kind of experiment with the climate. And you could argue that we're doing that now in the climate, because what we're doing is we're returning to the atmosphere the carbon that took, God knows how many tens of millions of years to bury, and we're returning it to the atmosphere in a couple of hundred years. It's like a big Green's function calculation. But we can do it in a model. So what I do is we take a model of the ocean. So this is based on the equations of fluid dynamics on a rotating stratified fluid, Earth, and we perturb it with this radiative forcing of a few watts per meter squared uniformly over the globe. And then we watch what happens and see how this system responds to that. And so what we do is we use an ocean model that's been developed by my group at MIT. And what we find is that the sphere of fluid on the Earth doesn't warm up uniformly. It warms up much more slowly around Antarctica than it does in the Northern Hemisphere. So the Northern Hemisphere warms up more rapidly than the Southern Hemisphere. And as you get closer and closer to Antarctica, it warms up less and less strongly. So we've got different response functions and different timings and magnitudes depending on geography. And this time scale of decades is controlled by the effective heat capacity of the ocean. So we can pass this, we can understand how this is working. So the warming patterns are not uniform, and so we can understand this. So here's a section through the ocean. This is a zonal average section. So this is the equator, North Pole, South Pole, and this is down to a depth of 2 kilometers. And this is the incoming radiative flux anomaly, which we've perturbed this. And that warms up the surface oceans. But because of geometry, essentially the ocean sinks in the northern North Atlantic and upwells around Antarctica. So there's this global overturning cell sinking in the north, upwelling in the south. And so what this does is it shunts the heat away from Antarctica, keeping it cool, and pushes the heat into the Arctic, warming it up. And that's fundamentally why the Arctic, I believe, is warming and the Antarctic is not warming as much, and in fact could be cooling slightly. So if we look at the global patterns of after 100 years, the sea surface temperature rises. Again, this is a numerical model, but this is the response function, the Green's function to a perturbation. And you can see that around the Southern Ocean, surface temperatures are hardly changing at all. And we see that in the data over the last 50, 100 years. The temperatures around Antarctica are not changing very much. In fact, they're slightly cooling. And the North is warming much more. In the data, you actually saw a little hole there in the warming tendency, which is the warming is delayed in the North Atlantic. And we understand that's a common feature of many of the climate change projection models, that the warming pattern, the warming is delayed in the North Atlantic. So the Arctic's warming up more than the Antarctic. Ocean circulation shapes the patterns of response. So I'm going to now go on to the last part and talk about the patterns. The Arctic warms up, I think, for reasons which are fairly straightforward to understand from first ocean dynamics principles. Now, this shows some observations of multi-year sea ice cover in the Arctic. This is Greenland. This is the median ice, summer ice extent. And over time, I'm going to show you some more recent data, but over time, the summer sea ice extent has been going down. And I think we may be moving into a world where we can move in the Northwest Passage across from the Atlantic into the Pacific in the summertime. So the Arctic ice cap has been thinning, opening up new shipping lanes, access to oil and gas fields, minerals, fishing in international waters. So if the Arctic does continue to melt, there'll be a gold rush. We're all going to end up moving there to try and extract resources. It's just human nature, isn't it? So this is a numerical simulation, a collaboration between JPL, not far from here, and MIT, and Patrick Heimbach and Dimitri Manomanelis configured this model. The model was built in my group at MIT. And so what I'm showing you is when we project the sphere onto the cube, we're looking at the pole at the Arctic cube, and what we're seeing is sea ice thickness. This is 5 meters. Pale blue is 1 meter. So this is in October 2007, and the ice is retreating. There's a seasonal cycle. So let me show you this to give you an idea that. So you see the sea ice is moving around. This is in the wintertime. The sea ice expands and it melts back. This is the Northwest Passage, and it expands again. This is a model where it's a large control problem, so there are observations of the ocean from satellite, observations of the ocean and sea ice, the interior ocean. And we define some kind of cost function which measures the mismatch between the model and the data. And then we use forward-backward methods to fit the model to the observations. So it is constrained by observation. Let me just show you that again. Just the ice fracturing and leading to leads in the ice. So the sea ice is very influenced by not just ocean temperatures, but by winds blowing over. This has been very recently released. This shows you, this is due to NASA, this shows you the multi-year Arctic sea ice as a function of time up to the present day, the last summertime sea ice. So, as in any natural system, there's lots of natural variability. It's going up and down, but it's basically going down. It did recover again and then bounce back. Okay, conclusions. What's happening and why? So we know that there are gappy observations, short time series, uneven quality. There are the uncertainties increase as a function of scale. So the global picture is much clearer than the regional picture. But the global picture is fairly clear, I think. That is that heat and CO2 from the atmosphere is going into the ocean. The ocean's warming up and it's becoming more acidic. And the atmosphere is, I believe, and 99.9% of people who work in our field believe, that the atmosphere is warming because of increased concentrations of greenhouse gases. I don't think the Senate actually voted on that issue, whether the warming was due to man-made effect, mankind. The oceans are warming. Why are the oceans warming? In response to an atmospheric change. The heat is coming from the atmosphere into the ocean. Sea levels rising. But there are very large uncertainties in what's going to happen because the big gorilla is the West Antarctic ice sheet, Greenland. This has to do with getting ice from the land into the ocean. And the physics of that is very poorly understood. We have very few observations of how glaciers are rubbing across, you know, the bedrock. It's very hard to model. And the ocean currents are changing. There's a there's something that you quite often see in the popular press. The Gulf Stream's going to disappear under. It's not true. The Gulf Stream is a wind-driven phenomena. As long as the winds are blowing, and they will blow even if we keep putting CO2 into the atmosphere for another 500 years, the winds will still blow. We'll still have middle latitude westerlies and trades, and we'll still have a Gulf Stream. But the ocean currents are changing because they reflect, they're intimately connected with the temperature field. The ocean has a cooling effect on the atmosphere. The ocean's taking heat out. It has a cooling effect on the atmosphere. Hiatus periods, these are to be expected and not surprising at all. I'd be staggered if the global mean temperatures just steadily rose. There's variability. The ocean takes up more heat in certain decades than others. It's a living fluid. It has its own variability. It's taking up heat, and it's not surprising there is a hiatus. The ocean's not passive in this. It plays an active role in setting the patterns and timing of warming. And there are polar asymmetries. In particular, I would expect, and I think we see hints of the fact that the Arctic is warming and Antarctica less so, or not at all. And the ocean is also becoming more acidic. Now, I know perhaps many of you are interested, indeed I am, but I don't know much about it, the life in the ocean. The ocean is becoming more acidic because CO2 is just dissolving into the ocean. That has implications for the biology and biogeochemistry of the ocean. Organisms that build shells are going to find it harder to survive in an ocean as it becomes more acidic. So we might see shifts in the biology and life in the ocean is changing. It's mainly changing because we're overfishing it, right, which is not a climate change issue. Thanks, MIT alums. I do want to, it is very much appreciated. I'm staggered by the community that you have here, how, you're together, you show up late at night to listen to these talks. It's very much appreciated.